Hi everyone, how are you? My name is Yonatan Wizman. I'm 29 years old. I am a backend developer at Dragontail Systems. I want to say that I'm very honored to be here today speaking. Thank you for the organizers and everybody that's given me the ability to speak today. Today we're going to be speaking about is effective memory management and the lost art of struct packing. Now in Go we have many... So in the Go language, we have a lot of built-in types, right? We have numeric different built-in types, all different types of integers. We have string, we have Boolean, right? We have the composite types. And also Go gives us the ability to define our own types, right? This is by using a struct, right? Everybody develops in Go knows you use type, the name of the struct you want to name in struct. The question is there any significance to the way that we declare the struct? It seems pretty simple. So that's what we're going to be diving into today. Hope you guys will bear with me and this will be as interesting to you as it is to me. So in this example, we see two structures, right? This is a packed struct and this is a padded struct. Now from now on, when I will be referring to a packed or padded struct, the packed struct is the optimal way of defining a struct, and a padded struct is the least optimal way. And I will, yes? Sorry. So the two structures, right? Well, I have one that's packed and one that is padded. The packed is the way that the structure should be defined in order to have the most optimal result, and padded is the less optimal results in terms of definition. So over here we see we have in these structs we have 8 variables of type bool, and we have 8 variables of type int64. The only difference between these two is in the packed struct, they're all defined one after the other. And in the padded struct, we have one bool, one int64, one bool, int64, interchangeably, right? So in terms of size, right, both structs contain 8 Boolean variables and 8 int64 variables. So technically speaking, this should be the same size, right? The basic math is we have 8 times 8 Boolean variables, which are a byte each, and we have 8 variables of type int64. We have 8 times 1 plus 8 times 8 should equal 72, right? But, however, by running the following program, we see this is not the case. The size of the padded struct, right, we said is the less optimal one. Again, reminding you guys, the padded struct is the one that was interchangeable. A bool and int64, a bool and int64. And the packed struct was the ones that were all defined together. One is the size of 128 bytes, one is 72 bytes. That's very strange. Why is that happening? So in order to understand, I'm going to be talking about 3 concepts. Data alignment, struct padding, and struct packing. So let's dive in. So the concept of data alignment is as follows: first let's talk about the problem. The CPU, right, wants to be able to read data or variable in its entirety in one CPU cycle. Now what's a CPU cycle? Depending on the architecture of the computer, whether it's a 32-bit or a 64-bit architecture, the CPU reads instructions in word-sized chunks. It doesn't read it byte by byte. So if you're on a 32-bit architecture, it'll read it in a word size which is 4 bytes. And if it is the 64-bit architecture, it'll be reading it in 8-byte word chunks. Now, in order to read the entirety of the variable in one CPU cycle, we need to make sure that the data is aligned. The data being aligned means that the variable will be at a memory location. Right, memory locations are numeric. At the memory location, it has to be divisible by the size of the variable. So say, for example, we have an int64, which is a size of 8 bytes. Then the int64 has to start from a location that is divisible by 8. So let's say right now I want to insert the int64 variable at location number 10. I can't because it's not divisible by 8. But I can insert it into location 16. All right? So how do I enforce this? How do I make sure that the data really is aligned, that it's starting from a location that is divisible by the size of the variable? So that's where struct padding comes in. Struct padding basically does as follows. In the scenario that I described before, where we have a variable of int64 that I want to insert in address 10, but I can only insert in address 16, so it allocates the space for the bytes from 10 through 15, leaves them empty, and then puts the variable int64 in address 16. That way it could read the word size chunk, which is 8. It'll read the whole variable of the int64, right? So this is very nice because it helps us really read a variable in one CPU cycle and not go into extra CPU cycles, which is very nice for us. However, this can be problematic in the event that we saw right now, right? We saw that we have more memory because of this concept of struct padding. So what can we do about this? So this is where struct packing comes into play. And this really is a matter of just being more mindful of how we declare our structures, how we arrange the fields, right? To make sure that we're not having the compiler pad too many bytes, not add extra memory. Now, the way we can do this is as a rule by thumb. The rule of thumb of doing this is we can put all the larger variables, right? First of all variables should be together, of the same type should be together. And then variables which are smaller should be at the ends. So let's say, for example, in the example over here that I gave with the booleans, it didn't really make a difference because I had 8 boolean variables and I'm on an 64-bit architecture, so it ends up being the perfect amount of padding. But the proper thing to do if we had a struct would be to put all the int64 variables first and then to put all the boolean variables. So two things: to put all variables of the same type together, and also to put the larger variables first and the smaller variables after. Now, sorry, any questions?
What about more complex structs? You need to start minding about their size?
I'm sorry, I didn't hear the question.
You have a struct that contains another struct. Those could get rather big.
I have to take into account that as well, yes. So there was a question asked right now, and was, if I have this struct contains internal structs, do I have to take into account the way this struct described as well? And yes, because, for example, if this struct was part of a smaller struct, right, then the smaller struct is part of a larger struct, then that struct would be 128 bytes versus 72 bytes if I hadn't packed it correctly. I hope that answers the question.
You talked about struct that is field or embedded struct?
Either way. Yeah. Sorry, so I had the question that whether we're talking about a embedded struct or an exposed struct, and it would be the same thing in terms of the memory footprint.
Another question: when you access a struct field, you don't need for your program, from the Go code, you don't need to know the position of the field inside the struct. You just access it by the name, right?
Right.
So why the compiler of Go not taking care of this optimization, because it knows the entire hierarchy of the sizes?
So that's a very good point. I completely agree. So the question was like this: if the compiler of Go already knows what is happening, right? Why does it not make this optimization itself? I don't know how to answer that question. I don't know why they don't do it that way. What you're saying makes a lot of sense.
I can give you an example. So when you're using explicit field names and reflection, this is right. But when you're using gRPC, going back to the previous question, gRPC is sort the structures by index. Okay, so you get a structure, you don't get the field names in structure like a JSON, you get them sorted out. So automatically sorting them every time you compile them may create gRPC incompatibility and other incompatibilities.
But you might sort them in formatting or
During
formatting using the equal to font.
Once again, I have a gRPC structure, okay, let's say int bool, int bool, int bool, int bool. Sorry?
When you have a gRPC structure, let's pretend, but you can't even add things in the middle of the struct anymore when you have already a gRPC.
Exactly. Now, if you create such a structure, you created such a structure from a gRPC using Proto C, Now, when you get the structure, you don't get a structure. You can't marshal it if Go would automatically optimize it.
So what happens in this event is, first of all, we have the element of the struct padding, right, which is trying to save us CPU cycles. So, you know, it would not be doing one or the other. Okay, so anybody else have questions? Okay. So I want to show like a visual example of what I mean. Okay, so here's the padded struct from before. Again, the padded struct is the least optimal way of doing it. Our first variable is of type Boolean, right? So that is over here, right? Then we have our next, right? So then we have our next variable, which is called number1, which is type in64. And I want to insert it inside the next memory address, right? And like, you know, it should be taking up basically memory from 9 plus 8 bytes, right? That shouldn't be a problem. But because of the data alignment concern, we cannot insert number 9, right? We can't insert in 10 or 11 or 12 or 13, etc. It can only be inserted into 16 because that is the next number that is divisible by 8, which is the size of the in64 variable, right? So what happens is, like we said, all this memory is allocated, right, but left empty. And then number 1 is put into the next address, and so on. This structure goes on. Happens 8 times because we have that sequence 8 times. Therefore, ultimately what's happening is for 8 times we're wasting 7 bytes of space, or allocating 7 bytes of space that we do not need, and henceforth using an extra 56 bytes of space. 128 bytes instead of 72 bytes. Okay, so in this example now we have the pack struct, right? We output the first Boolean variable in number 8. And we put the second Boolean variable in number 9, right? Because the size of a Boolean variable is 1, so it could be inserted anywhere. And so far the whole way down, right? And then we want to input our first in64 variable. We see that it's already divisible by 16. Now, technically speaking, there's also something called, I happen to set up this example to work perfectly because I know that I'm working on a 64-bit architecture. I know that I have, this will be 1 word, 8 bytes, and I know I have 8 variables. So let's say, technically speaking, if I had 6 Boolean variables and 6 integer variables, I would have 2 bytes of padding, meaning it would take from all the way from 8 to 13, and then these 2 bytes would be padded because the integer variable would not be able to be assigned to any divisible address. It's like 16. But I just built this example to make to show. Any questions? Okay, so the following question is, why does this concern me? Like, what do I care? Okay, right now CPUs are so powerful, I have so much memory. Like, okay, fine. So I'll take it. I'll take the extra 56 bits. Like, what does it interest me? What do I care? Right? So first of all, that's not always true. Sometimes you have memory concerns, right? Let's say you're working on an embedded system. Let's say you have, for some reason or another, you have memory concerns. We should at least know how this works. In addition to that, sorry, yeah, exactly. You're paying for all that. Now, in addition, what if we could argue that there was actually an effect not only in the amount of memory that's consumed, but rather an effect on the performance itself? What if I told you that the way you arrange your structs, the way you declare fields in the structs, actually made your code faster or slower? So, first of all, I want to explain this argument theoretically, and I want to explain, right? So, let's say we have in this example that we just gave right now, right? We have the padded struct and we have the pack struct. The padded struct we saw was a size of 128, right? 128 divided by 8, which is the size of a word cycle, right? It means it would require 16 CPU cycles in order to read that structure, right? As opposed to the 72 bytes pack struct, which would only require 9 CPU cycles. That's very significant. CPU cycles basically means the more CPU cycles, the more time it will take. we're talking about literally double the amount, almost double the amount of CPU cycles to fetch the same structure with the same fields. Okay, so I want to take a look at a following use case just to sort of explain a little more. So we have a server, right? This server is taking 1 million requests per minute, right? Doable. And this server has a 2 gigahertz, the clock speed is 2 gigahertz, which basically means that a CPU cycle will take 0.5 nanoseconds, right? So based on our example, right, on this, in case we have to unmarshal every a million requests. In the case of the padded struct, we have to basically marshal 128 bytes times 1 million, which would be 128 million bytes, right? And in the second scenario, with the 72 bytes, we are marshaling 72 million bytes, right? Now, the padded basically will take 0.5 times 16 million CPU cycles, right? You have 128 million, well, the same numbers as before, just with millions. So 16 million CPU cycles will take basically 8 million nanoseconds. And the 72 bytes will take 8 million CPU cycles, which is 4.5 million nanoseconds. And they're saying, okay, 4.5 million nanoseconds, 8 million nanoseconds is true, it's almost twice as much time, but that's, it's a small amount of time, it's not such a big deal. But when you scale and things get larger, or the CPU requests come 1 million requests a second, that can become a lot more problematic. So like I wrote over here, padded takes 8 million nanoseconds, and the pack takes 4.5 million nanoseconds, almost the amount. Okay, so I made a video of a benchmark, but I think I'm just going to run it live. First of all, I want to show the code. All right, so I have a benchmark. I have a struct of the example good, which is the padded struct. I made the fields a little bit larger to show. Each struct has, structure 1 has 54 elements of type int64 and 64 elements of type byte. And I just want to show what this function does. So I create a struct of example good, and then I go through all the variables, and I basically input all of them, right? I'm basically initializing the values. That's all this function does. I want to show that the initialized padded struct does the same thing, right? So here are two functions that do the exact same thing. The only difference between them is one is using the example bad, right, the padded struct, and one is using the pack struct. Now let's see if this has an effect on the performance. That has a very, very significant difference on performance over here. And the only thing we did was change the order of which we declare the fields in the struct. Like when I realized this personally, to me that was crazy. Okay, anyways, moving on. So now I want to discuss some sort of edge case. And this won't usually happen, but it's definitely something that needs to be taken into consideration, especially if your CPU resources are not very strong. You don't have a lot of CPU resources. Your program may be running locally, right? This is an edge case that won't always affect us, but it's definitely something to take into consideration. And in order to do this, I want to give a bit of a high-level overview of virtual memory. All right, so over here what we see is a picture of virtual memory. right? Over here is we have our program address space, right? Our program basically has its own address space. It's not the same as the physical memory, let's say in RAM or in disk, right? And what happens is that there is a map, right? That we map the program address space to a physical space, which is either RAM or disk or cache, but we're not going to get too much into that, okay? Well, let's say that I can't find my instruction in the RAM, right? What if the instruction is in disk? So basically this whole really complicated thing happens. We receive something called a page fault exception, right? An exception is raised by the CPU hardware. Sorry. And after that, we call the page fault instruction handler, right? We basically have to choose one of the instructions that already are running in RAM that we don't need anymore, and we have to remove it from RAM. Then we need to check that this instruction, we didn't modify the memory in any way. If we did, we have to write this memory back to disk. We have to fetch the new instructions from disk, put them back, add them to RAM, right? We have to update the page table. The page table is basically the mapping between the program instructions and the program instruction memory and the physical memory of the computer. Now, this is really, really, really slow, meaning a page fault instruction is basically the slowest thing that could happen, except for maybe human interaction for the computer. That is literally the slowest thing that could happen. Now, granted, right, this is a lot more relevant or a lot more serious if we're working with like a hard disk drive. And, if it's a hard disk drive, then it's about 1,000 times slower than getting the memory from RAM. And if we're working with SSD, then it's maybe between 5 to 20 times slower, but still very, very substantially slower. So I want to argue something. What if we had a scenario, right, that the amount of RAM that we have, right, for our computer was not enough for the program that we're running, right? In that event, we would have to have this page fault exception a lot more frequently. We would have to go into disk to fetch these instructions, and they would run incredibly, incredibly slow. Now, this may sound crazy if we're working with big, powerful servers in the cloud, and we may not have that issue, but I've seen programs, right, run locally on 32-bit machines with 4 gigabytes of RAM, right? And the program in its entirety size was actually bigger than that. And that would require going to disk, reading more. So first of all, it could be with this, like a smaller struct size, right? If we really minimize that, we would need really half the amount of RAM, or let's say 56% of the RAM. And therefore, we wouldn't even get to that situation possibly. But let's say we are getting to that situation in any event, the page fault would happen a lot less frequently. Remember we were talking about CPU cycles in the beginning? And we said that, the difference in 2 CPU cycles, fetching a page fault exception takes about 80 million CPU cycles. Remember, do the math, 2 gigahertz CPU clock, 0.5 nanoseconds, 80 million CPU cycles, 40 million nanoseconds. That's tremendous. And again, while this is something that we're not usually dealing with because we're dealing with these big, powerful servers that usually allot us the right amount of RAM, like first of all, like you said, comes at a price. And second of all, we have to be mindful of sometimes there's scenarios where that could happen. Any questions?
I can say that it actually can happen even with today's powerful servers, because when you run several pods in the same cluster, you want at some point to limit the memory of each pod, and then they get out of memory killed, and then or you increasing the memory, and then you can run less pods on the same cluster. So even today, memory constraints can give you the ability to run more pods on the same hardware or to pay for a more expensive one. So super relevant.
And usually autoscales are using either CPU or number of requests. So even if you have an autoscaler, then the autoscaler would not identify memory, let's call it leak, such memories, so the pods would be killed and other pods would not come in place.
Yes. It's definitely very, very important to be mindful of, declaring these structs, because it may take us a few extra minutes to do, but we can save a tremendous amount on performance. So to summarize, the data alignment is basically the concept that the CPU uses a certain mechanism called padding in order to ensure that the data is read its entirety in one CPU cycle, right? Like we said, padding is the agent that is making sure that this is happening. Now, struct packing is the way for us to avoid the extra padding. And we said a few rules of thumb is bunch all the variables are the same type together and put the larger variables first and the smaller variables last. In addition, the size of the struct, like we saw, can add a considerable amount of performance, not just in terms of memory concerns. It could add a massive, massive concern also in terms of performance. We saw in the code, in terms of the benchmark, was the padded benchmark was more than 100% slower, right? And as far as the edge case, which is something that is very possible to happen, but maybe not so frequently, is the element where really you're using more RAM than we have for, and we can have a lot more page faults, and this would cause considerable effectiveness of the program. Thank you guys very much. It was a pleasure speaking to you, and if there's any more questions, happy to answer, and it was my honor being here tonight. Thank you.